So in this video, I just wanted to go over some of the basics of benzene. We've talked about benzene as far as being just a group and what it looks like, but I want to talk a little bit about the physical and chemical properties of benzene. All right, so first of all, if you were to look at benzene, you might just think of it as cyclohexane. So if you drew a six-membered ring, all right, that would be cyclohexane as long as it had all single bonds. All right, you might think of benzene is just cyclohexane with 3 double bonds in it. All right, but there's evidence to indicate that that's not really how it exists. All right, one of the forms of evidence has to do with bond lengths. All right, what we know about the average carbon-carbon single bond is that it's got 0.154 nanometers of length. All right, the average double bond would be 0.134. All right, and so if benzene were to actually exist like this, you would expect that this bond right here would be longer than this bond right here. But what we actually know about benzene is that all of the bonds are exactly the same length. All right, and that bond length is actually somewhere in between a single bond length and a double bond length. All right, so what that indicates is that with benzene, you got something a little bit different going on. You have a situation where the bonds are somewhere in between a double bond and a single bond, and not only that, they're all the same. All right, so even though you draw it like this, every single bond in this molecule is the same as any other. And one way that that's shown is through a resonance structure, where you can show it alternating with these bonds being in these new positions right here. All right, since these two are both acceptable structures, a lot of times benzene is drawn just with a circle in the middle. So you draw a cyclohexane ring, but then you put the circle in the middle, and that indicates one of these structures right here. All right, so the next little bit of evidence had to do with hydrogenation experiments. All right, so we talked a little bit about hydrogenation of alkenes earlier, and essentially when you're doing this, you're treating an alkene with hydrogen, and you need some sort of catalyst. I believe we talked about palladium as a catalyst earlier, but nickel can also be used. All right, so this is an exothermic reaction. All right, it gives off 120 kilojoules per mole heat. All right, so if benzene were nothing but cyclohexane with 3 separate double bonds, you would expect the amount of energy given off when you hydrogenate this to be 3 times as great as this, because there would be 3 times the number of double bonds. But what you find is that that number is minus 210 kilojoules per mole. That's the amount of heat that would be given off. And notice that that's not quite 3 times as much. All right. So the reason for that is that this is a relatively stable structure. All right. Each of the bonds in this molecule is more stable than this bond right here. All right. So one more bit of evidence is the fact that when you have 1,2 disubstituted benzenes, all right, for example, this is 1,2-dichlorobenzene, you don't have 2 separate isomers. All right, so if we drew these structures as if they were essentially 3 separate double bonds, this would be a different isomer from this. All right, and one way we know that is that if you know anything about NMR, this molecule right here, if it were actually to exist this way, would have what's called a coupling constant between these two H's right here, which would be fundamentally different from the ones that you have for this molecule right here. All right, so the fact that we don't see this type of what's called coupling in the NMR spectra indicates that this isn't really the way these things exist. In fact, they don't exist like this or like this. They kind of exist as something in between. All right. So The last little bit of evidence is that benzene rings don't readily undergo addition reactions. All right, they more readily undergo what are called substitution reactions. All right, so just a quick review. We talked about this with alkenes, but with an addition reaction, you essentially are adding all of the atoms and electrons. Every little piece of this bromine gets added to this molecule right here. All right, so if you counted up all the atoms and all the electrons, you'd find you have the exact same total here. All right, and notice one other thing about an addition is that during the process of an addition, you end up losing a bond. All right, so this goes from a double bond to a single bond. All right, in a substitution reaction, and by the way, this would not actually happen with an alkene. I'm just showing this hypothetically to show what the difference between a substitution and an addition is. With a substitution, essentially you're doing just that. Your two atoms are changing places. All right. So if we treated an alkene with bromine and let's say that it did undergo a substitution reaction, one of these bromines would substitute with this hydrogen right here. All right. Notice that puts a bromine here, and you would have left over HBr. So where does that H come from? It would have come from this hydrogen right here. So notice that if I were to draw this just like this, it would look like you're just adding a bromine right here. But remember, it's a substitution, because when this happens, you would have had a hydrogen here that is no longer there once you get to this molecule. All right, and it's a little bit easier to see if I draw that hydrogen in right there. All right, so if we take benzene and we treat it with bromine, and you're going to need this aluminum tribromide catalyst, or I guess this would be just aluminum bromide. If this were to undergo an addition reaction, what you would notice is that you would get two bromines added, and you would end up getting rid of that double bond. All right, because remember, in an addition reaction, you lose that double bond. All right, but instead, what you get is you only get what would be considered monosubstitution. You only get a bromine on one of the carbons, and you also generate HBr as a byproduct. All right, so the fact that this does not undergo the type of reaction that you typically see with alkenes is evidence that this molecule here is more stable than it would be if it was three separate double bonds.